Okay, I guess everything looks good and we can start. Hello, everyone. Thank you for coming here. Thank you for joining the lecture one more day. Today, we're going to give, at least for now, our last lecture on processing in memory. And we actually are dividing this lecture into two parts. In the first part, we are going to talk about the UPMEM PIM architecture, which is, as you know, the first real-world processing in memory architecture, and we are going to present the benchmarking work that we have conducted on this architecture. Why is this interesting, or why do we believe that this is interesting? Because this is the first in-depth analysis of a real-world processing in memory architecture. So that's why we consider that this is interesting to you. And then in the second part of the lecture, we are going to talk about another of our recent works, which is a data movement characterization, data movement methodology for characterization of data movement bottlenecks. Both are very recent studies, and both are related to the series of lectures that we have been giving in the last 3 days. So yeah, let's start with this one, lecture 9A. If you have any questions over the course of the lecture, please feel free to raise your hand and ask. If you're in Zoom, you can type the questions in the chat, or the same in YouTube, and the scribes will for sure ask me the questions directly, or I can check them myself. So before we go into the UPMEM case study itself, we are going to very, very briefly recap on what we have seen in the previous 3 lectures. First of all, Professor Muldu talked about major trends affecting main memory and about the need for intelligent memory controllers. And then we introduced the 2 main directions in processing in memory. The first one is what we call processing using memory. The second one is processing near memory. As you will see today, we are going to talk about the UPMEM PIM architecture, which is a good example of processing near memory architecture. And we finished the past lecture talking about the different things that need to be developed in order to enable the adoption of processing in memory. Very, very quickly recap on the papers that we presented in the 2 lectures ago about processing using memory. You may remember that the first work that tried to do something using memory, using DRAM, was this row clone paper. The idea is essentially to send 2 activates commands to memory in order to enable the direct copy from one row in a subarray to another row in the subarray with a very simple sequence of commands, 2 activations, and 1 pre-charge operation or 1 pre-charge command. We can have a very fast copy and initialization inside the DRAM subarray, which you may remember might be up to 2 orders of magnitude faster and higher energy efficiency than the normal operation via the host CPU and the cache hierarchy. Second work on the topic is this fast bulk bitwise and OR in DRAM. That was the seminal work of Ambit, which is the first processing using DRAM proposal, first processing using DRAM mechanism. As you may remember, this is based on the idea of activating 3 rows at the same time in the same subarray, and this way we can perform a majority operation. And by using the majority operation, we can implement other logic operations and more complex operations, as well, as you may remember from the SimDRAM paper. This is an extension of the Ambit paper. This is a very interesting work, Compute DRAM, that already showed that even in off-the-shelf chips, it's possible to execute row clone and even Ambit operations by playing with the timing parameters of DRAM. And we have also seen how processing using memory is also applicable to other memory technologies. Pinatubo, for example, presented at DAC 2016, is a good example of that for phase change memories. And this is the SIMDRAM framework that I mentioned before that gives us the possibility or gives us the ability to create new instructions, more complex than the ones that were presented in the original AMBIT paper. So this is the first trend in processing using memory. There are, other trends as well. We were talking about, for example, crossbar arrays based on MBM memories. It's what we typically call MBM PIM, and it's also like a very exciting trend. And the other main approach is processing near memory. In this case, instead of operating directly with the memory cells, as we do in AMBIT or we do in RowClone, we operate on processing elements that are placed near the memory array. For example, a DRAM subarray, we can place a compute unit near to it, or near the bank. We are going to see today the UPMEM example. But very, very quickly recap on the different papers that we discussed in the previous lecture. For example, this is the Tesseract paper, which is one of the, I would say, classic papers on processing near memory. This proposes a coarse-grained accelerator for graph processing based on 3D stack memories. As you may remember, the idea is to have an accelerator that is composed by multiple memory cubes. In the logic layer of these memory cubes, we have a number of in-order cores that can communicate among each other and have access to the graph and can also surrogate operations to other cores in order to perform the graph processing operation. Another example is this Google workloads for consumer devices. Here it's a interesting work, as you may remember, where we perform a characterization of these workloads in order to show the need for processing in memory in mobile architectures, mobile systems. There are, as you may remember, different parts of the consumer applications that show a lot of data movement, and one way to alleviate this data movement is using processing in memory. So that's why, so that's the approach that is taken here in this paper. Difference between the previous accelerator and the things that are proposed here. In the previous accelerator, we are offloading a whole application onto the accelerator, the coarse-grained accelerator. However, here, what we are doing is offloading functions or smaller kernels, right? So that's one way of doing processing in memory or processing near memory. And then we also talk briefly about a couple of proposals for processing in memory for GPU architectures, which follow similar approach as well. We are going to have 3D stack memory. In the 3D stack memory, in the logic layer, there are some simplified GPU cores, and we offload either whole kernels to these simplified cores or sequences of instructions that result to be highly memory bound in the execution on the conventional GPU cores. And then another interesting work, also I would say seminal work in processing in memory, or at least in the recent research in processing in memory in the last 5-10 years, is this PIM enabled instructions, which is like proposing a minimal support for processing in memory. As you may remember, the idea here is to identify some instructions that can benefit from being executed closer to memory because they are especially memory bound. And these can benefit many workloads, for example, graph processing workloads, right, where we typically have very low arithmetic intensity, but very scattered memory accesses, like random memory accesses that cause a lot of cache misses in the cache hierarchy of a conventional architecture. And after that, we also presented a few works that are in the direction of enabling the adoption of processing in memory, because you may come up with a nice idea, okay, let's offload this operation onto memory, and let's see theoretically, right, or even in simulation, that we can provide some performance improvements, some energy savings, But when it comes to reality, we have to take into account many more things if we want to make an end-to-end integration into the real system. And one of the things to take into account when you have concurrent execution on the memory side and from the host side, so you have both processing in memory cores or processing memory accelerators and regular host CPU or GPU accelerators accessing the same data structures in memory, we should provide a way of maintaining memory coherence, right? And that's what this lazy PIM work is about, and also this extended version of it, which is Conda, quite recent as well, in ISCA 2019, as you may remember. And yeah, it's a kind of an optimistic way of maintaining memory coherence that results in very good performance, very close to the ideal. But maintaining memory coherence is not the only thing that we should support in the system. Synchronization among PIM cores is also important. Essentially in a PIM system, you're going to typically have many cores, and in these cores maybe running one or multiple software threads, and these software threads may need to synchronize, right? And then this is especially important in multi-threaded applications. So that's not an easy task because, as you may remember, one typical way of synchronizing different threads is using a shared level of cache or a shared main memory, but processing in memory systems may have more like the appearance of a distributed system, right? And in that case, we don't have a shared memory space, so we need to come up with different ways of doing it. And this is a hardware-based message passing approach that also results in a very nice performance and energy savings. And there are even more things, right? Like supporting virtual memory in processing in memory systems. There is, for sure, more to do in this direction, but this is one paper that approaches this problem and proposes one solution, as well as this other one, how to design efficient concurrent data structures for processing in memory. And it's not only that. If we want to enable all of these different things, we have to do research. And in order to do research, we need an infrastructure, right? That can, so that requires in part simulation infrastructures and in part appropriate codes to do our analysis. So regarding simulations, one thing that I talk about is about the RAMulator simulator and its extension for processing in memory that we call RAMulator PIM. After releasing this, we released a new version of this simulator that is called the MoveSim and comes from this work, a new methodology and benchmark suite for evaluating data movement bottlenecks, which is what we are going to cover in the second lecture today, in lecture 9B. And then even more things that are useful to evaluate processing in memory systems, like, for example, these machine learning-based performance and energy models that we also presented a couple of years ago. But anyway, as you already know, if you want to review all these different proposals and all the different challenges that still need to be solved in order to enable the adoption of PIM and end-to-end integration in computing systems, I would recommend you this book chapter where you can find all of these, and as well this shorter version, which is a journal paper, or this other one, it's another journal paper. So by doing all of these, not only Safari Research Group, but many other research groups in the world, in industry and academia, we are enabling the paradigm shift. And even though, you know, this technology started 50 years ago or so, or the idea of using processing in memory started 50 years ago or so, it's only now in 2019 when some company, UPMEM, a French startup, released this processing in DRAM engine. And we are going to talk about it today. This is a nice picture of the PIM-based system, or UPMEM PIM-based system, where you can see two CPUs and then some DRAM DIMMs that represent, where is my cursor? Represent main memory, as you can see here. And then we also have some PIM-enabled memory, which are these UPMEM DIMMs here. And UPMEM is not the only company that is making progress in the direction of enabling real-world processing in memory systems. We have the Samsung FinDRAM. I'm pretty sure that you have already seen this slide several times. It's FinDRAM is based on the 3-stack HBM2 memory. And as you can see, it's composed by some storage layers or some pure memory layers and some FinDRAM layers, where we have something like this. We have memory banks. Here you can identify bank 0, bank 1, bank 2, bank 3. And between two banks, what we have is this PCU block, which is a processing using memory, so processing in memory unit. And actually, this is near bank processing in memory or processing near bank. And it has many similarities with the UPMEM PIM architecture that we are going to present, but it also has some differences, of course. The one key difference is that the UPMEM PIM architecture is more general purpose, and as you will see, it has quite a rich instruction set architecture, while UPMEM, while Samsung FinDRAM is more application specific, right? It's targeted to AI and machine learning workloads. So it has a much more reduced instruction set, mostly multiply, accumulate, and add operations and some data movement instructions as well. And this is another proposal from Samsung, more recently announced, is AXDIMM, which has been tested for recommendation systems, and it's a DIMM-based solution. So here, instead of like in FinDRAM or in UPMEM, we have the processing elements near the banks inside the memory chip. In the AXDIMM proposal, we can also say it's near memory because we have the memory chips here, and next to them we have this AXDIMM buffer where the compute elements reside. If you want to learn about these architectures, we are talking about them in one other course that we are teaching on processing in memory. It's every Tuesday, 7 p.m. We live stream the lectures. So if you are interested, you can learn a little bit more about all of this. Do you guys have any questions about the previous slides or previous lectures? So if not, I think that we can go ahead and start with the this lecture 9A, Understanding a Modern Processing in Memory Architecture, or this case study of analysis of a real-world processing in memory architecture that is called UPMEM. Let me start with a brief executive summary. You already know that data movement is dominating performance and energy consumption in computing systems these days, and processing in memory is a way of tackling with this memory data movement bottleneck. But even though it was proposed many years ago, as you know, there were multiple technology challenges that prevented from the materialization of this technology into commercial products, right? And UPMEM, as I said before, is the first company that has fabricated real-world processing in memory system. It consists of DDR4 chips, as you just saw in a previous picture. And inside these chips, we don't only have DRAM subarrays, but we also have small processors that are called DRAM processing units, or DPUs. We are going to see how these DPUs work internally today. And here in our work, what we are presenting is, first of all, an introduction to the UPMEM programming model and PIM architecture, a micro-benchmark-based characterization of the DPU in order to study what are the architectural limits of these processors, how fast they can run, essentially. And then we do a benchmarking and workload suitability study. So we already know that there are certain characteristics of the workloads that make them potentially suitable for processing in memory, right? Like, for example, random memory accesses or low arithmetic intensity. We have seen in previous lectures the example of PageRank or other graph processing algorithms. But that's the theory, let's say. When we go to the real world processing in memory architecture, we have to analyze it better and see what workloads can really benefit from this architecture, because in the end, they have their own constraints and restrictions, right? And that's something that we are going to talk about today. So main contributions of our work are the characterization of the PIM architecture and analysis of the PIM architecture, and from our benchmarking and workload suitability study, there is a byproduct, which is a benchmark suite. The first benchmark suite for a real world processing in memory architecture that is called PIM, and it's composed until now by 16 workloads that are memory bound in conventional processor-centric systems. You will see later how we select these workloads. We analyze the performance of these workloads on the UPMEM PIM architecture by using strong and weak scaling experiments. I will briefly mention what that means later if you don't know, I mean, you're not so familiar with the terminology. And we also compared the performance of the PIM system with state-of-the-art CPUs and GPUs. Key takeaways of our work are the workload characteristics for PIM suitability, programming recommendations, suggestions and hints for hardware and architecture designers. This is also something interesting from the analysis, is that we are going to identify what are the weaknesses of this architecture, right? And we can propose ways of improving the architecture or other processing in memory architectures for the future. And finally, the PIM benchmark suite, which can be used, for example, for the purpose that I just said, improving processing in memory systems, but also they can be useful as programming samples, right? For people who want to learn how to program one processing in memory architecture like this. This is just a little bit of motivation. I think that this must be clear so far. Probably you're even familiar with the picture. We have a lot of data movement in current computing systems. This is an example of a system on a chip, and there you have certain numbers, percentages of the total energy spent on data movement for different types of applications like consumer, scientific, or mobile applications. So the goal here is to make compute systems more data-centric, as you know, and processing in memory is the way of doing it. And this is again the picture of the slide that you have seen before is with this picture here of the UPMEM DIMMs containing a number of chips, typically 8 or 16, and inside each of these chips is where we have memory arrays, as you will see, and DPUs, DRAM processing units. Before we go into the details, I want to give you one of the key takeaways of our work. Why do I want to show this to you? Because even though we are going to see, as I said, some strengths and some weaknesses of this architecture over the course of this lecture, I want to highlight what are the potential, what are the benefits that we have really measured on the real system on a significant amount of workloads and in comparison to the state-of-the-art CPUs and GPUs, including high-end GPUs as a Titan 5, which is quite a new one. So one first takeaway here is that the UPMEM-based PIM systems, we test 2 UPMEM-based PIM systems in our study, outperform state-of-the-art CPUs in terms of performance and energy efficiency. And you can see we are talking about more than 20 times faster performance, faster execution on the larger processing in memory system compared to the baseline CPU implementations for the 16 PIM benchmarks. Compared to state-of-the-art GPUs, GPUs for sure are more powerful, right? They have much more peak throughput, much higher peak throughput than conventional CPUs. So that's why we don't observe here such large speedups, but still for 10 processing in memory, for 10 PIM benchmarks, we see more than 2.5 times faster performance on the UPMEM-based PIM system. And the outlook is even more positive for future PIM systems. Why do we say that? Because you have to put things in the context, right? We have been working with CPUs and GPUs for decades. and improving the software, improving the way we write software for them, and improving the way they work internally, improving their hardware and their architecture. You can simply go to, for example, a comparison of NVIDIA GPUs over the last 10 or 15 years. I can tell you GPUs started to be used for general purpose computing around 15 years ago in the when the CUDA framework was released back in 2006, 2007. And if you compare the performance of a current GPU with one of those first GPU computing or general purpose GPU computing capable GPUs using CUDA, you will see that it has improved several orders of magnitude, right? So we are comparing a technology that just started and to technologies that have been developed for decades. So it's just a matter of waiting a little bit of time to see this more positive outlook for the future, right? And yeah, last takeaway here is that the reason why processing in memory systems are faster or can be faster and more energy efficient than CPUs and GPUs is because both improvements are coming from the same reason, right? Which is the large reduction in the amount of data movement, because now we are operating closer to where the data resides. So if you want to learn more after this lecture, you can check our papers. This is some like short version of our work, and this is the longer one. Both are publicly available at arXiv. And over the course of this presentation and also the papers, you will find some banners like this one with programming recommendations, key observations, and key takeaways. I wanted to show them to you here in advance in order for you to identify the different messages that you're going to receive over the course of this lecture. I showed you the papers, but all our codes are also publicly available, micro benchmarks, and even the scripts that we have used for our experiments, they are available in our repository. Okay, so yeah, let's start with the outline of this lecture. So first of all, we are going to start with an introduction to an overview of the UPMEM-based PIM system. Then I will give you very introductory concepts about how to program an UPMEM PIM system, because I believe that, I mean, it's very short thing, but I think that this can be useful to understand the way that we do our plan for our experiments and the way we do our analysis. Then we are going to talk about the architecture of the DRAM processing units, and we are going to characterize this DRAM processing unit, measure, for example, what's the arithmetic throughput for different types of operations and data types, and also bandwidth to the different memory spaces that the DRAM processing unit has access to. Then we are going to talk about our benchmarks and the evaluation of these workloads and comparison to CPUs and GPUs. And finally, we are going to give a few takeaways. Okay, so let's start with the introduction and the overview. Okay, yeah. It's a little bit slow. What can we do? Maybe we need processing in memory here, right? Okay, let's start with the introduction. The UPMEM-based PIM system is based on what we call the accelerator model. What is that? So in the accelerator model, we have conventional DIMMs that coexist with UPMEM DIMMs. And the way that we integrate these UPMEM DIMMs is by considering them as an accelerator or a coprocessor for the main processor that is typically a CPU, a host CPU. So we see these UPMEM DIMMs as a loosely coupled accelerator. And what this means is that we need to explicitly move data from the host processor to the accelerator. In this case, from the memory of the host processor, the CPU, and the memory of the accelerator, which are the PIM-enabled memory, PIM-enabled DIMMs. And then we also have to explicitly launch the kernel execution on the UPMEM processors. In some sense, this resembles GPU computing. If you guys are familiar with GPU computing, especially if we are using discrete GPUs, we have to do this. First of all, we need to copy the input data from the main memory of the CPU to the global memory of the GPU, then launch the execution of the kernel on the GPU, and then when the kernel finishes, we can retrieve results and bring them back to the main memory. One important difference here is that in a discrete GPU, in a heterogeneous system with a discrete GPU, the way that we typically move, or the channel that we typically use to move data from the main memory to the GPU, to the global memory of the GPU, is by using some bus, external bus, like PCI Express or maybe NVLink in some NVIDIA GPUs and systems based on NVIDIA GPUs. While in the UPMEM PIM system, even though the way that we operate is similar because we have to explicitly move data, we are using the memory channel. So supposedly we are able to achieve, or we should be able to achieve, higher bandwidth as well in this data movement. We don't have a very detailed evaluation of this bandwidth and no comparison for now to the data movement for NVIDIA GPUs, because in reality, this is not fundamental to the architecture itself, right? So it's something that will eventually improve as well as these memory buses or communication channels keep improving as well. So, and if we take a look at the system organization, this is how it looks. You will typically find in an UPMEM-based PIM system, you will find a host processor, a CPU, and then some DIMMs of DRAM, for example, regular DDR4 DIMMs that are going to be used as the main memory, same as usual. And then we have some other DIMMs that represent the PIM-enabled memory. So these UPMEM DIMMs typically contain 8 or 16 chips, and every 8 chips, we call them a rank. So we are going to see 1 or 2 ranks per DIMM, and inside each PIM chip, there are 8 memory banks, 8 DRAM banks of size 64 megabyte, and we call these banks main RAM, or for short, MRAM. And then attached to each of the banks, we have 1 DRAM processing unit or DPU. So in total, there are 64 DPUs per rank because there are 8 DPUs per chip and 8 chips per rank. And we are going to talk about the internals of the PIM chip later, but yeah, you can already see here the MRAM bank. This is one of the 8 MRAM banks, and then we can access this MRAM bank using this DMA engine from the pipeline of the DPU in order to move instructions from the DRAM bank to this instruction memory, or operands from this DRAM bank to this WRAM, which is a scratchpad memory that we can, it's kind of a cache that we can handle in software. We, as the programmers, can decide when to move data, bring data or operands from the DRAM to the WRAM. And after having operated on these values, writing the results to MRAM. It's, as I said, similar to the way one hardware cache operates, but here all the control is on the programmer's hands. And this is one of the UPMEM-based PIM systems that we have used in our study. It's composed by 20 UPMEM DIMMs, so in total 40 ranks, and you can see it's a dual socket CPU, and each of the CPUs has access to its own main memory and PIM-enabled memory. In total, this system can have up to 2,560 DPUs, and something interesting as well is a size of up to 160 gigabytes, which is pretty large memory capacity. If you compare this, for example, to the typical size of a GPU these days, you will see that it's like 4 times bigger at least. I think it's 4 times, because if I'm not wrong, the A100 has 40 gigabytes, right? And also much more expensive memory, because that one is HBM, while this one is DDR4. And here you can see again the picture of the the large UPMEM-based PIM system with the 2 CPUs. These are the DRAM DIMMs for CPU 0 and CPU 1, and these are the PIM enabled DIMMs. Okay, and we have also experimented with a smaller system. In this case, it only contains, 10 UPMEM DIMMs of 8 chips each. These DIMMs correspond to a older version of the UPMEM DIMMs, but yeah, still 640 DPUs and up to 40 gigabytes of memory, PIM-enabled memory in this system. Okay, so after the introduction, let's talk briefly about how to program the UPMEM-based PIM system with a very naive example, vector addition. And we are also going to talk about the communication between the host processor and the DPUs and the processing in memory cores. This is our first programming example. We are actually not going to see code here. It's just like I want to explain you how we partition the computation essentially, and how we distribute the computation over this large number of DPUs. You have seen more than 2,500 DPUs, and also internally inside each DPU, we will have multiple threads running, right? So we have to partition the whole workload in some way over these DPUs and tasklets or software threads. So in vector addition, as you for sure know, we have 2 input arrays, A and B, and what we perform is the element-wise addition of A and B in order to calculate the values of an output array C. So we have, so this is kind of a simple programming example, right? Because here we can evenly partition the input arrays and the output array across DPUs. So this chunk here would be assigned to DPU 0, that one to DPU 1, this is for DPU 2, and this is for DPU 3, assuming that in our system we only have 4 DPUs. And then internally, inside each DPU, we use software threads that run on this same core, and they are called tasklets. I just want to have this name here because I will repeat the name tasklet several times, but you just think about them like software threads. And then so this whole chunk that has been assigned to DPU 0 should also be distributed across the tasklets. So assuming that we have 2 tasklets in each DPU, one way of partitioning can be this one. This is for tasklet 0, this is for tasklet 1, and we do the same in the rest of DPUs. One thing that you can observe here is that all tasklets have an ID, which is important for the tasklet to know which part of the array it has to process, right? We are going to address that by using the ID of the tasklet. This is tasklet 0, this is tasklet 1. And then when we go to another DPU, you can observe that the IDs of the tasklets are the same because these IDs are local to the DPU. Okay? Are there any questions so far? Okay, so general programming recommendations. These are programming recommendations that we found in some documents from the vendor, from UPMEM. The first of these general programming recommendations is that we want to execute on the DRAM processing units portions of parallel code that are as long as possible. Okay, observe this recommendation. It's first of all portions of parallel code. Of course, it's a parallel architecture, right? We have multiple cores, and in each of the cores we can have multiple or several software threads. So we obviously want to run parallel code on the DPUs, and then also that they are as long as possible. This relates to something that for sure you're familiar with, which is the Amdahl's law. The amount of speed up that we can achieve from a parallel system depends on the fraction that we are offloading, executing onto the parallel units, right? So that's why we want to run sequences, so portions of code that are as long as possible. Second programming recommendation is to split the workload into independent data blocks, which the DPUs operate on independently. Why is that? Because remember, this is kind of a distributed system. Each DPU has its own memory, its own NRAM bank. So what this means is that if you want from a DPU to access data, the fastest way to access this data is if the data resides on the same bank, right? So that's the reason why this is the second programming recommendation. And actually what you will see very soon that in case that we need a DPU to access data that is stored or it's being produced by another DPU, it's going to be quite costly because this is going to require data transfers that go through the host processor. As you will see, those are not, those are going to represent kind of an overhead here. And then recommendation number 3 is to use as many working DPUs in the system as possible, which is also some interesting recommendation. You also, related to what we said in the beginning, we want to run large portions of parallel code, and also we want to exploit this parallelism as much as possible. So if you have 2,000 DPUs in your system, try to use them all. In some of the cases, you may end up, I don't know, operating on a relatively small input data set. In that case, it might not make sense to use a super large number of DPUs, but in principle, that's the approach. The fact that we have multiple DPUs in the system has an additional advantage, is that we can have several processes or multiple processes running on the host processor and using these DPUs. The DPUs are not shared by different processes, each individual DPU, and there is no reason for that because we have thousands of DPUs in the system. So what we can do is dividing them into different groups of DPUs and assigning them to the different processes. And finally, launch at least 11 tasklets, which are these software threads per DPU. You will see why. I'm not going to advance anything yet. Okay, so how the CPU communicates with the DPUs using transfers. We are going to call them CPU-DPU and DPU-CPU transfers for obvious reasons. This is a CPU-DPU transfer when we copy something from main memory to the PIM-enabled memory, and this is a DPU-CPU transfer. And the SDK, the UPMEM SDK that we use to program this system gives us different ways of performing these transfers. One way is doing them serially, which means that from the main memory, we are only targeting a single DPU and a single MRAM bank. So we transfer a buffer from main memory to one DPU. That's not the most efficient way of doing these transfers. It's much better to do parallel transfers because this way we can transfer different buffers to different banks and do it at the same time. So we should expect higher bandwidth from these parallel transfers. And then the third type is the broadcast CPU-DPU transfers. In this case, we are transferring, it's a broadcast operation. We are transferring the same buffer, the same data from the main memory to all DPUs or to multiple DPUs at least, those that we define in this transfer. And so you may be asking yourself, oh, okay, so these are serial, these are parallel, these are broadcast. So let's try to use these ones, right? Because we should expect higher bandwidth from them. And whenever we need to communicate from the main memory to the PIM-enabled memory, let's try to use these ones. But it's not always possible. Why is that? One current limitation of the parallel transfers is that the size of the buffers that you transfer from main memory to PIM-enabled memory or vice versa, or in the opposite direction, should be the same. If you have irregular buffer sizes, you should use serial transfers. That's a current limitation of the UPMEM SDK. I believe that this can be solved in future versions of the SDK, but this is why we still need to use the serial transfers. And there are benchmarks or there are workloads where this will happen for sure. For example, this is one of our benchmarks, select, which is a relational algebra operator you might be familiar with. Here, in this select operation, this example, what we are doing is removing even values. You see one input array, and this is the output. The predicate is true if it's even, and if it's even, we remove it. We don't copy from the input to the output, right? Imagine that we have 3 DPUs in our system. We can do uniform partitioning of the input and assign the same number of elements of the input array to the different DPUs. Because these chunks are of the same size, we can use parallel transfers. But then the output is depending on the values of the input. So if you look at this chunk, you will see that there are 2 even values that we remove. So we only copy these 2 to the output, while here only one of the 4 values is odd, right? And that's the only one that we are copying. So this makes that we have to transfer different sizes from the memory of the DPUs or the PIM-enabled memory to the main memory, and that's the reason why we have to use serial transfers here. And you will see actually that when we evaluate this workload, in the results, you will see that these serial transfers take a significant amount of time. And the data transfers are also important because they are also the way to synchronize or communicate across DPUs, what we call the inter-DPU synchronization communication. This inter-DPU communication takes place via the host CPU using CPU, DPU, or DPU, CPU transfers. And this is, for sure, one current limitation of the system. Why is that? Because this is going to be costly, much more. So in the end, the bandwidth that we have here is much smaller than the bandwidth that we have here, right? So when we are moving data from here to there, the problem that we have is that we are incurring in the data movement bottleneck because we are using this narrow memory bus. So that's why, it's important to evaluate what's the cost of these transfers, and it's also important to think for the future how we could, in future processing in memory systems, avoid this bottleneck. For example, this is a DRAM chip, right? And inside the DRAM chip, you could do row clone. So it might be possible, for example, for 2 DPUs inside the same chip to share data by using something like row clone or something like Lisa, for example, which is another processing or copy using DRAM technique that I explained like 2 lectures ago. So these are, ideas for you to think about how to optimize these or other processing in memory systems. We have in our study different communication patterns. For example, merging partial results to obtain the final result. You may have some computation being done here, 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 and so on. For example, generating a histogram. You have a large image, you divide the image into different parts, tiles or chunks, and you assign them to different DPUs and have each DPU creating a subhistogram. And then you bring all subhistograms to the host CPU for merging the subhistograms into a final histogram. So that's one possible communication pattern, simpler one. More complex patterns require redistribution of intermediate results. For example, you have a, say, graph processing algorithm that is iterative, right? And after each iteration, you have certain intermediate data that you need to redistribute. For example, to ensure load balancing across DPUs. That could be one potential reason, right? So in this case, we need data transfers from the DPUs to the CPU, then do the redistribution, and then move data back, intermediate results back to the PIM-enabled memory. So it's a more complex communication pattern, as you can see. But how fast are these data transfers? Well, we evaluated this by creating a micro benchmark, a simple program that performs different types of transfers from the CPU to the DPUs and vice versa. And in particular, we run two different experiments. In the first one, we use a single DPU. And what we do is changing the transfer size, either from CPU to DPU or vice versa. And as you can see, we change it from 8 bytes to 32 megabytes. And in the second experiment, we use one whole rank. One whole rank meaning 8 chips, right? Up to 64 DPUs. So what we are doing is measuring how much the bandwidth changes when we increase the number of banks from 1 to 64. And we will see, for example, that in parallel transfers, the bandwidth increases. Yeah, so we also did some preliminary experiments with using more than 64 banks, more than one rank, and we detect that the system is exploiting channel level parallelism, right? So you have several memory controllers in the system, and they can be moving data from the MRAM memories to the main memory in parallel. So the system is able to exploit channel level parallelism to get even higher bandwidth for this communication from main memory to the MRAMs and vice versa. Something that I mentioned before is that we expect that this operation suffers the data movement bottleneck. Why is that? Because we are using the memory bus. So the maximum that we can achieve here is the maximum bandwidth that you can achieve in a system with DDR4 memory. But as I said before, and related to one of the programming recommendations, we want to run sequences of portions of parallel code as long as possible. Why is that? Because we need to transfer data from here to there, right? And this means this entails an overhead, and we want to amortize this overhead. So the way to amortize the cost of these transfers is by computing more on the DPUs. Okay, so let me show you some results for the first experiment with a single DPU, where we change the data transfer size from 8 to 32 megabytes. These are the results for CPU, DPU transfers. These are for DPU, CPU transfers. And the very first observation here is that larger CPU, DPU transfers result in higher sustained bandwidth. So we can better exploit the bandwidth that the memory bus provides to perform this communication between the main memory and the MRAM banks. The larger these transfers are, the better, right? Well, at some point you see that the bandwidth saturates. So obviously there is a limit that is imposed by the DDR4 bandwidth, as I just said. But yeah, in principle, we will get more from something like 32 megabytes rather than 8 bytes only. So that's something that we observe. Second set of experiments is for a whole rank, and here we vary the number of DPUs from 1 to 64, as I said. In the plot, you can already see the bandwidth results. So I forgot to say that this is bandwidth in logarithmic scale, and these are the results for the serial transfers, CPU, DPU, and DPU, CPU. Because they are serial, we are targeting one MRAM bank with every transfer, right? And this happens serially. So we are not increasing the bandwidth. So that's why the bandwidth remains constant. As we target more DPUs or more MRAM banks, and we execute the transfer serially, the total time increases. And that's why the bandwidth is constant. But if we go to parallel transfers and broadcast transfers, you can see that they increase with the number of DPUs. And actually this broadcast transfer, this 16.88 gigabytes per second is very close to the theoretical bandwidth, maximum bandwidth of DDR4 memories, which is around 19 gigabytes per second. So we are not doing that bad here. And a key observation is that the sustained bandwidth of parallel CPU, DPU, and DPU, CPU transfers increases with the number of DRAM processing units inside the bank. The more DRAM processing units or MRAM banks we are targeting with a transfer, the more parallelism we achieve, and this way higher sustained bandwidth. And you can find more details in our paper. Okay, now we are going to talk about the architecture, microarchitecture of the DRAM processing unit, and also the ISA a little bit. We are going to describe it. internally, and then we are going to characterize it with some micro benchmarking experiments. Okay, you already know this picture, the host CPU system, main memory, PIM enabled memory, and inside each of the PIM chips, we have multiple DRAM banks. If we look at the internals of the PIM chip, we find two interfaces. The first one, DDR4 interface, is for the host, the CPU processor, to access the NRAM banks, same as we have in conventional DDR4 chips as well. And then we also have a control status interface for the CPU to communicate with the DPUs. Why do we need this? Because we need the CPU to have the ability to tell the DPUs, you start computing this, right? And also we want the DPUs to inform the host processor when the kernel terminates. I'm done with my task, you can continue the execution. This is something normal in the accelerator model that this UPMEM-based PIM system follows. Here on the right-hand side of the picture, you can see the 61 of the 64 DRAM banks, MRAM, one of the MRAMs, and the DMA engine to access it. And by using this DMA engine, we can either move instructions from the DRAM to this IRAM or operands between MRAM and WRAM. What's the difference between these two? Well, the first difference is the size. They are both SRAM-based memories. This is of size 24 kilobytes. That size allows us to have up to 4,096 instructions in this IRAM. Notice that this is not an instruction cache, as you can find in CPUs or GPUs these days. This is an instruction memory. So we need to move the instructions, or we need the runtime system to move instructions explicitly from here to there. Actually, they first come here, but they are definitely coming from the host, right? Which is where we create the programs, and then we move the program to the DRAM bank, and then from the DRAM bank to the IRAM. And here we have the WRAM of 64 kilobytes. It's called WRAM or working RAM, and it's a scratchpad memory. I don't know if you guys are familiar with scratchpad memories, but in some sense they are like a software managed cache. Instead of having some hardware units taking care of what data is placed in the cache, we give this ability to the programmer. The programmer has full control on what we place here, right? And well, this might be a little bit more cumbersome or complicated for programmers, but also gives us the possibility of being more efficient than caches, right? And recall that, for example, one of the reasons why we observe this data movement bottleneck in current computing systems is because existing ways of alleviating the data movement are not so efficient for many important workloads. For example, one way to detect that a workload is memory bound is by checking what's the number of misses in the cache hierarchy. For example, the MPKI is one of the metrics that we will talk about in the second part of the lecture. So yeah, if you have full control on the data that you move to the on-chip memory, to this faster memory, you may be able to achieve more performance. And then we have the DPU pipeline. So let me show you more details about the DPU pipeline. This is an in-order pipeline, no out-of-order execution. In current UPMEM-based PIM systems, it runs at a frequency of up to 350 megahertz. This is expected to be a little bit higher in the next generation. And it's a fine-grained multi-threaded pipeline. What this means is that we have multiple threads. We have multiple hardware contexts, one of them for each of the threads. And each of these hardware threads essentially execute the software threads that we define using our programming model. In a fine-grained multi-thread architecture, as I said, what we have is multiple hardware contexts or architectural contexts. In the end, what this means is that we have a register file that is partitioned, and each of the parts is assigned to one thread. And we also have multiple program counters. And what this means is that we can have threads running on this pipeline, each of them executing its own program because they have their own program counter. So when it comes to schedule one new instruction, we are going to go, so we have, you see there, the first stage of the pipeline is a dispatch unit. This dispatch unit will decide what's the next thread to schedule and what's the instruction for this thread to launch an issue onto the pipeline. How to do that? The dispatch unit selects the thread and then checks its program counter. Okay? Yeah, then you can count and you will see that there are 14 pipeline stages. Some of these stages are like multi-cycle stages. For example, we need 4 cycles for the ALU or 3 cycles for the read operand stage. Yeah, you may be familiar with fine-grained multithreading already if you have taken introductory computer architecture courses, like for example, digital design and computer architecture. But if you need to recap or you need a refresher on the topic, I would recommend you this lecture given by Professor Mutlu the past spring. Okay, so now that we know more or less how this fine-grained multi-threaded pipeline works, we are going to analyze it with a little bit of detail. And to do that, we created a micro benchmark. In this micro benchmark, we analyze the arithmetic throughput for different operations and data types. We stick to a single DPU. The reason is that we have multiple DPUs in the system, but they all work the same way. And we use a cycle counter to perform our measurements. This is the micro benchmark. Actually, as you can see, it's pretty simple. We go to WRAM, bring some data, and then perform some computations on the data. This is for 32 integer addition, but we also have multiplication, division, and so on. And this is the compiled code, let's say. So you can here check in detail, and you will see the correspondence of the individual instructions. These are the instructions from the DPU ISA. You can find more details about this in the UPMEM documentation. And here you can see the results and also the reason why we are going to use typically 11 tasklets or more in our programs. These are arithmetic throughput results for different number of tasklets from 1 to 24. And here you see integer 32, 64, floating point, double, and for different operations, right? So these are addition, subtraction, and then multiplication, division. These are the results for the rest of data types. And the key observation here is that in all cases, the saturation point of this throughput happens when the number of tasklets is 11, right? This relates to the length of the pipeline. You remember the pipeline has 14 stages? Well, the pipeline can issue 2 instructions from the same tasklet every 11 cycles. So that's the reason why we see that the throughput saturation point happens at 11 tasklets. One more observation is that integer 32 is a little bit faster than integer 64. And we can understand why this happened by checking the code. We can actually obtain the theoretical arithmetic throughput if we know the frequency of the DPU, 350 megahertz, and we know the number of instructions that we need for each of these operations. And we can do some compiler analysis of this. Recall our micro benchmark. This is the micro benchmark for 32 bits. This one is for 64 bits. And on the right-hand side, you see the compiled codes. The difference between these two is just a single instruction. This 8C, because there we are operating on 64 values. So what this means is that we need to move the carry in the addition, the carry out from the lower 32 bits of the addition to the upper 32 bits. And this is why we need this extra addition instruction. So we have 6 instructions for the 32-bit micro benchmark, 7 for the 64-bit micro benchmark. And this is what explains the peak throughput. Sorry. So around 58 mega operations per second for 32 bits, 50 mega operations per second for 64 bits. And more observations here. This is the high throughput difference between addition, subtraction, and multiplication and division. And the reason is that the DPUs don't have a 32-bit multiplier. They only have an 8-bit multiplier. And the way that they implement 32-bit multiplication or division is by using other instructions that may take more than one cycle, up to a maximum of 32 cycles indeed. And yeah, one reason for that is the difficulties of creating compute units using the DRAM technology process, right? So that's why this doesn't mean that a 32 multiplier is impossible to have near the bank. It's possible for sure, but as you can guess, UPMEM designers and engineers had to make some design decisions, and this is one design decision they made. And then also we see that something similar happens when we compare the performance of integer operations with floating point operations. And in this case, it's because of similar reasons. The way that floating point operations are implemented is not with native support, is not with native floating point compute units, but by emulating by software. And this is why we see lower performance there. Okay, then we measure also what's the bandwidth to WRAM from the pipeline. And to do so, we also create one micro benchmark. In particular, we create the stream micro benchmark, which is a very common way of measuring peak bandwidth for different types of operations in memory for different computing systems. You can find versions of the stream benchmark for CPUs, GPUs, etc. And that's what we did here in this analysis of the WRAM bandwidth. Let me very briefly show you these micro benchmarks. It's a very simple thing, as you can see. We access a certain array in memory, and from memory, in this case in WRAM, and then we go in a stream and in a streaming access. So accessing all elements one by one for in this case, 2-3 buffers that we have in memory, and we may perform some operation or not. So in the first case, it's just copy, as you see. In the second case, it's an addition, and then we write to an output array, buffer C. This one is a multiplication, and this one is a multiplication and addition. So we measure the bandwidth of WRAM using this operation. This is for copy, this is for add, this is for scale and triad. The more operations, arithmetic operations we perform, the lower the bandwidth, as you can expect. And we can also, estimate what's the bandwidth, and also compare it to all measurements. So the values that you see on the plot are measured values, and now we can explain these measured values by using this analytical expression. The WRAM bandwidth is the number of bytes that we move multiplied by the frequency of the DPU divided by the number of instructions that we are using in each specific operation. So for example, if we focus on copy just uses 2 instructions, a WRAM load and a WRAM store. We read one value from WRAM, we write it back to another position in WRAM. So it's only 2 instructions. If it's only 2 instructions and we are using, for example, 11 tasklets, with these 2 instructions, we are moving 16 bytes per tasklet. So in total, we are moving 11 times 16 using these bytes here, using a certain number of instructions. And this way, we obtain 2,800 megabytes per second, which is very similar to what we are measuring, right? In our paper, you can find more results, also more analysis for the other types of the other versions of the stream benchmark. And yeah, we don't have time to go over all of them into a lot of detail. Okay, second thing that we analyze here is the access to MRAM, the DRAM bank that is near each of the DPU. So here is where we are, and we are going to perform different types of measurement as well. One first thing that we are going to measure is the latency of the bandwidth, the latency of the DRAM axis. If my computer wants to go to the next slide. Okay. Yeah. Yeah, okay. Yeah, we are going to waste the lecture on this. This is amazing. I think Zoom has a real problem. Yesterday I was using another tool, I think, what is it? Google Meet, and this didn't happen. However, in Zoom, it's always a problem when you're sharing the screen with you know, a PowerPoint. So yeah, first thing that we measure is the latency of a single DMA transfer, because this is going to be pretty useful to reason about the bandwidth results that we measure with different access patterns. First of all, a stream benchmark again, but now not to WRAM, but to MRAM, and then strided and random access patterns. You for sure know what's a random access pattern. A strided pattern is when two consecutive accesses are, let's say, regular, but always at a certain distance, and we call this distance the stride. Yeah, I don't know what to do. I really apologize. I don't know if I'm going to restart or I'm going to, maybe I can even have time to go to Bahnhofstrasse and get a new laptop. I don't know. You know what? Yeah, that's definitely a good idea. Yeah, not sure what to do. I will just share again. Well, yeah, okay, I will try. But this is really annoying. Okay, what we did here was measuring the MRAM read and write latency. We use, you know, the API that the SDK provides to or to perform, to order these transfers from MRAM to WRAM or vice versa. These are what we call MRAM read and MRAM write, and we measured this and we also obtain the MRAM bandwidth for each individual transfer by using the MRAM latency and then the size of the transfer and the frequency of the DPU, as the expression shows. And one thing we observe is that we can model the MRAM latency with a linear expression, something like this thing that you see here, alpha plus beta time size. And actually, you see that the model, which is a thin black line on the plots, matches pretty well our measurements. And from the measurements and from the model, we can obtain that this beta equals 0.5 cycles per byte, which is essentially the bandwidth that MRAM provides when moving data from WRAM to MRAM or vice versa. And this means that the theoretical maximum MRAM bandwidth on a single DPU is 700 megabytes per second, which is actually like a very promising number if we take into account how many DPUs we can have in the same system. So one key observation here is that we can model the access latency to MRAM linearly with a linear model, and also the theoretical maximum bandwidth of MRAM is 2 bytes per cycle. Okay. One other observation. read and write accesses are symmetric. They essentially achieve the same latency and bandwidth, and also that the bandwidth increases as we use larger transfers as well. So as far as possible, one programming recommendation is to use large transfers, large DMA transfers, if we want to exploit higher bandwidth, right? From the
sorry to interrupt. Can you hear me?
There are more programming recommendations. Yeah, I can hear you.
So there's a bit of an issue with the audio on Zoom and YouTube. You're really broken up, and the video feed as well. So I'm not sure if you want to consider rebooting the machine, or because otherwise it's affecting the recording also.
No, I don't think that's a good idea. I mean, I can do that in the break, but not right now.
The thing is that and it seems to be getting worse a bit. So
do you know if the YouTube live will keep moving if we restart the laptop?
Yeah, I can stop the live stream and then.
But when you resume it, will continue in the same video.
The live stream. This is too cumbersome. It's not very convenient. Yeah, okay, I think we are going to have a break here. But once it's not as planned, but we are going to have a break here, and let's do it in 10 minutes because probably we're going to be short of time today. So yeah, I really apologize for the inconvenience. Let's make it 8 minutes. Yeah. Yeah, give me 1 second.
When I was using and sharing from Zoom, I don't know if it was memory, but when you check you can see that it's quite a lot, and it's why it slows down the magnetize.
Yeah. This is
it's an issue with
first,
Zoom.
I'm going to stop the live stream and then try to review it and so on. Okay. Yeah, well, we're going to continue now. Let's see if we are luckier this time. Okay, so yeah. So we were talking about the different experiments that we did to measure latency and MRAM bandwidth, and so MRAM latency and bandwidth. And in the second experiment, we measured the bandwidth of the stream benchmark. No, that's not going to happen. Okay, you had an idea, right? Okay. Yeah, if you have any questions, please let me know in the meantime so that we can use this time.
You showed that 64-bit operations are somehow much slower than 32-bit operations.
Well, not much slower. They are slightly slower because they are using one more instruction.
Yeah.
7 instructions instead of 6. Or you mean the floating point compared to integer operations?
No, that was exactly one operation more. So for that,
okay.
What I didn't understand, there was either, I think it's either the ALU bound, so we're twice as slow because we use twice the number of ALU operations, we're not ALU bounded, then the pipeline are not slower at all, which is why I would expect either half the speed or triple speed.
So the first thing to take into account here is that it's not only the individual ALU operations, additions in this case, it's also that we have to access the operands, and this requires to go to WRAM and then write the results back to WRAM. Okay. Second thing to take into account here is so you need, in the end, this is a pipeline execution, and in every cycle we are retiring one instruction that has been completed from a different thread, right? So here the assumption could be that you are going to have a whole addition completed every 6 cycles or 7 cycles, depending on what's the specific operation. So it is pipeline, but in the different stages of the pipeline, you are so in the different cycles, you are issuing different instructions from different threads, right? So in the end, the effect is that the total number of cycles that you need to perform one addition in this case is 6 or 7, and that's why the throughput is different in these two cases. Okay. So if you were, because we are considering a single addition for a single thread, if you were considering the execution for all threads at the same time, as soon as the pipeline is full, you are retiring one instruction every cycle, and you could, let's say, perform a different measurement, let's say, or measure the throughput in a different way. But we wanted to focus here on a single tasklet, or on a single operation for a single tasklet. Okay, maybe in the meantime I can try to continue. I don't know. This is completely blocked. You see? And I don't know if it makes sense to use start video. I don't care at this point. Okay, can you hear me in Zoom?
We can hear you. Yeah.
Okay, very good.
Can you just switch the displays? We see the presenter view.
Yes.
But everything else is fine, I think.
Okay.
Good, perfect.
Okay. Yeah, now it's students in the lecture room who see the presenter view, but I guess it's fine at this point. Okay, so as I said several minutes ago, we were talking about how to measure bandwidth and latency of NRAM. And we have already seen how we measure the latency and even the fact that we can come up with a linear model for NRAM. And now we are going to measure the bandwidth. In this case, we use the stream benchmark. It's exactly the same code that we have used for WRAM, but in this case, we include the transfers to MRAM, right? Or from MRAM. So this MRAM read and MRAM write. And we actually have two different versions of copy. The first version streams through the array in WRAM, as you can see here. In the second one, it only uses the MRAM read and MRAM write APIs. So here you can see the sustained bandwidth for different number of tasklets from 1 to 16. This is copy DMA, and we see that copy DMA saturates at 2 tasklets. The bandwidth saturates at 2 tasklets, and after that the bandwidth is constant. And why is that? Well, the DMA engine in reality can only support a single transfer at a time. It's not, so we are not exploiting memory level parallelism here as we can have in a GPU when we are using multiple threads, or a CPU when we have multiple threads accessing memory. Here it's just a single transfer. But when we are using 2 or more tasklets, we guarantee that there is always a tasklet ready to issue a new MRAM read or new MRAM write. And that's why the bandwidth is slightly higher. We can also analyze the bandwidth of copy and add. The previous one was copy DMA, this one is copy and add. And here you see that the saturation points happens at a different number of tasklets, 4 or 6. And also for a scale and triad, it's 11 tasklets, which is something that we could expect from our previous experiments with related to the arithmetic throughput, right? But we can try to explain why this happens. The reason why copy and add saturate at 4 tasklets or 6 tasklets is because that's the number of tasklets for which the latency of the MRAM accesses becomes longer than the pipeline latency. So imagine you have 4 tasklets and you are issuing requests to MRAM for data movement from MRAM to WRAM, one after the other, right? And at some point, because these DMA transfers are serial, we are increasing the latency of all these operations together. But at the same time, we have execution of arithmetic operations for copy, which are the accesses to WRAM, or add, or scale, or triad. We are executing these instructions in the pipeline. The pipeline is pipeline, right? So in the end, when we increase the number of threads executing, the number of tasklets executing on the pipeline, we are not really increasing that much the total pipeline latency. Why is that? Because it's pipeline, and as we were discussing before, we are going to terminate one instruction every cycle. So in the end, at some point, this balance between latency of memory accesses and latency of pipeline execution changes. And this happens for 4 or 6 tasklets for these 2, or it happens at 11 tasklets for the other 2. And that's because scale and triad, the execution of instructions in the pipeline, it's always longer than the accesses to MRAM. So the interesting observation here is that we can distinguish between 2 types of workloads here. Ones are the memory-bound workloads, are those like copy and add, where the access to MRAM takes longer than the execution in the pipeline. And that's what we call a memory-bound workload on this architecture. And then we have a compute-bound workload on this architecture when a particular workload takes longer to execute on the pipeline than what the memory access take. And then we also have strided and random access patterns that we have studied in our analysis for the strided access patterns. For example, we used 2 different ways. I'm going to go very quickly over this because we have wasted too much time. But yeah, anyway, the key idea here is that there are 2 different ways of doing the strided access patterns. One way is say, okay, let's go. So you may remember that the longer the transfers from, or the larger the transfers from the MRAM to the WRAM, we can achieve higher bandwidth, right? So based on that idea, one potential way of doing the strided transfers, strided accesses, is by bringing a whole chunk of data to MRAM, to WRAM, sorry, and then perform the strided accesses in WRAM. Good thing of that is that WRAM is pretty fast. We can get 1 value every cycle. But the problem is that we are not going to use all the data that we are moving, right? Because we are accessing in stride. And that's what we call the coarse grain strided access. If you think about it, in some sense, it resembles the way that caches work, right? Because when you are performing accesses on a CPU, for example, to memory, you are bringing whole caches of 64 bytes. And you may not be using all 64 bytes. Maybe you are accessing just a couple of elements, maybe, I don't know, 16 bytes in total, right? So, but it's more or less based on the same reasoning. The second way of doing the strided accesses is a fine-grained access, where we only bring the individual elements that we are going to use. Problem here is that if we are accessing, for example, only 8 bytes, and then another 8 bytes, and then another 8 bytes, we are using much shorter DMA transfers, and we don't exploit so much bandwidth, right? So this is also for the future to think about how to optimize the performance of these. And here you can check see some results comparing coarse grain strided accesses with fine grain strided accesses. And in the end, what we observe is that at some point for certain stride, the fine grain strided accesses become more efficient than the coarse grain strided accesses. And this is essentially because we are bringing a lot of data, but we are only reading maybe 1 every 16 elements or 1 every 32 elements, or even less from the whole thing that we are bringing. So the effective bandwidth goes down and down and down. So that's what we observe for strided access, random accesses. And one programming recommendation from this is, based on what we see, we may prefer one way of accessing data or a different way of accessing data for our program. Last thing that we analyze with respect to the architecture of the DPU is this analysis of the arithmetic throughput versus the operational intensity. So here we also write a micro benchmark, and in this micro benchmark we include both accesses to MRAM and also computation in the pipeline. But for the computation in the pipeline, what we do is changing the number of operations. We are going to use a variable number of operations, arithmetic operations. In that sense, in that way, we are changing the operational intensity or arithmetic intensity of our micro benchmark. The more additions or the more multiplications we perform on every individual data element that we bring from MRAM, the higher operational intensity. And this analysis is based on the roofline model, which is a very common workload characterization methodology. So, well, this is the micro benchmark. I think we can skip it, but yeah, essentially what you can see is MRAM read, MRAM write, and here in the middle we have a number of repetitions, which is the number of times that we execute the same operation on the same data to change or increase the operational intensity. And here we see some results for different data types and operations, in particular addition multiplication for 32-bit integer and floating point operands. But in the end, more or less, the key observations here are quite similar for all the workloads. Notice that y-axis is the arithmetic throughput in logarithmic scale, and here we have the operational intensity. And the number inside each of these dots is the number of tasklets that we are using in our analysis. So this is the performance or the throughput for 2 tasklets. And if we increase the number of tasklets, as you see, the throughput doesn't change. So what this means is that the arithmetic throughput saturated with 2 tasklets. Why is that? Because this is very similar to just a pure copy operation, right? Observe that the arithmetic operational intensity is super low. It's only 1 operation every 2048 bytes. So it's almost nothing. It's just like a copy operation. And that's why it's memory bound and it saturates with less than 11 tasklets. And we observe same trend for higher operational intensities. And at some point, it starts saturating with 3 tasklets. Remember, copy and add saturated at 4 and 6 tasklets respectively, right? So here we are showing similar observations in a different way. Notice that the throughput doesn't change for higher number of tasklets. And then this continues happening until this operational intensity of 1/4, and then it really starts saturating at 11 tasklets, and then their maximum arithmetic throughput just remains constant. So we distinguish between 2 parts here: the memory bound region, where the arithmetic throughput increases with the operational intensity, and the compute bound region, where the arithmetic throughput is flat. And this point in the middle is the throughput saturation point. The throughput saturation point is very low. It's low, even in this case, it's even lower for other data types and operations. For integer additions, is 1 integer addition per every 32 element. So every 32-bit element. So as you see, it's a pretty low, and it's even lower for others. Okay. Yeah, but the observation is very similar. Now, very briefly, let me talk about the benchmarks that we have developed for this architecture. We selected these benchmarks for multiple reasons. I mean, those are just goals of having a benchmark suite for the UPMEM PIM architecture, something that I mentioned before, having sample codes for people and also for programmers, and evaluating the architecture, and also for comparison of software or hardware improvements. And then 2 key selection criteria. First of all, use applications from different domains, and then also that they are, at least in principle, what? Yeah. If they can hear me, it's enough at this point. So yeah, memory bound workloads on processor-centric architectures, and in total we have 16 different benchmarks, because we have for 2 of them, for 2 of the workloads, we have 2 different versions, like for example, this image histogram and this prefix sum. And here you see the list of benchmarks for different domains like linear algebra, databases, graph processing, neural networks, and so on. And we select, as I said, the workloads by using the roofline model. All of the workloads for a CPU fall in this side of the roofline, that is the memory bound area of the roofline, because it's limited by the by the access to data. We consider that this area here is the compute bound area of the roofline. To the left of that elbow, for example, we can call it, to the left, it's the memory bound region. So all of these fall in the memory bound region. And they are also diverse, the benchmarks, I mean, diverse in terms of memory access patterns, computation patterns, and communication and synchronization patterns. Go ahead. Yes, you can use the microphone.
Is it purely incidental that all the compute bound, all the workloads ended up being compute bound on
the CPU? On what?
That they ended up being compute bound on UPMEM. So they're memory bound on CPU.
Yes.
But it looked like they're all compute bound on UPMEM. Was that intentional?
What you're saying is true, but I haven't shown that yet. No. No, the previous plot is the roofline model for the CPU, for Intel Xeon CPU. Okay. No. That L3 is the bandwidth that L3 provides. But yeah, what you say makes sense, and we are going to explain why. As I said, we have different patterns in the different benchmarks, so they have some diversity, different communication and synchronization, either intra-DPU synchronization that we can, we can synchronize tasklets inside a DPU using barriers or mutexes or handshakes, and also some of them require inter-DPU synchronization. And as you can imagine, this inter-DPU synchronization is going to entail a certain overhead. In some of the cases is more or less lightweight, in other cases is much bigger overhead. And let's evaluate the workload. So we do strong and weak scaling experiments for both. What's the difference between strong and weak scaling? Strong scaling refers to how the execution time of a program solving a particular problem varies with the number of processors for a fixed problem size. So I have this array, and then I have a number of processors. How do I partition this array into for 2 processors or 8 processors or 64 processors? So this way I see how the performance scales when I increase the number of processors for the same problem. And then weak scaling is when the problem size per processor is fixed. So if I use more processors, I also use a larger problem because the problem per processor is fixed. So that's essentially the difference. It's 2 ways of measuring the scaling. And we use them for 1 DPU, 1 rank, or 32 ranks. Actually, we only have results because in the end, the insights are more or less the same. As you can see, I'm not going to go into many details in this talk, but you can later see in the paper, weak scaling is only for 1 rank. And then we also have the comparison to state-of-the-art CPU and GPU. And the data sets, this is the list of data sets for 1 DPU or 1 rank, 32 ranks, and also the weak scaling data set. And yeah, all of this is available in our repository. And here you can see some results for a single DPU. Well, these are the results for the 16 workloads, the 16 benchmarks. As you can see, we changed the number of tasklets from 1 to 16. These are, for example, for vector addition. And this is the execution time on the DPU for a single DPU. So as we increase the number of tasklets, we reduce the execution time of the kernel for obvious reasons. Inter-DPU synchronization time, in this case, there is no inter-DPU synchronization time for vector addition. The time to transfer input data from CPU to DPU, and then transfer the final results from DPU to CPU. And also we show the speed up. This red line shows the speed up for the execution of the DPU kernel. So some observations here are, okay, so the best performing number of tasklets is always 16 in most of the these experiments, in most of the benchmarks. And this is in line with what we could expect from our analysis of the arithmetic throughput of the DPU. You remember that it saturates at 11 tasklets. So it makes sense. We are not testing 11 tasklets here, 8 or 16. So that's why we see that the highest performance is obtained with 16 tasklets. But you could check yourself that the performance actually saturates at 11. This is also quite slow. Okay, yeah. More observations. Some of the workloads don't use intra-DPU synchronization primitives, which is great for their scalability. In other cases, for example, these ones here, there is synchronization, but this synchronization is pretty lightweight, so it's not really affecting the scalability, while in other cases, the scalability is limited because we are using, more complex ways of synchronizing different tasklets, like, for example, mutexes for these 3 benchmarks that are surrounded by a red square. And we can actually take a closer look at one of them. This is the histogram. It's one of the versions of the histogram. Here, what we do in this version is we have one whole subhistogram, one subhistogram per DPU. So what this means is that all tasklets running on the same DPU access the same subhistogram. And the way to access the same subhistogram is by using a mutex. In the end, I think you should know what a histogram is. It's a way of counting the different types of occurrences of whatever thing that we have in an input data set. For example, if we have an image, in the image we have multiple pixels, and these pixels have different values, right? For example, if that's a monochrome image, is the luminance value. So we create a histogram, which is a count of the, for each of the possible values that the pixels may have. It's a count of the number of pixels that have certain value. That's a histogram. So if we want to create that histogram and do it correctly, we need to update in an atomic way, meaning that we cannot have two threads or two tasklets trying to update the same being of the histogram, the same counter of the histogram, right? They have to first go one and then go the other one. That's why we use a mutex here. And then the problem with using mutexes is that this limits the scalability. And you see how the performance with 8 tasklets is better than with 16 tasklets. But it's because of the use of this synchronization primitive, this mutex in this case. And then we have another example. Well, this is some interesting observation here. In this case, for example, it's one of the kernels in scan SSA, one of 4 versions of prefixum. It uses one simple kernel that is called add. And in add, what we observe here is that there is no scaling from 8 to 16 tasklets, but add doesn't have any, it's not using synchronization primitives, right? So why is this happening? Well, the thing is that the amount of computation in this add operation is very lightweight, almost no computation. Recall a stream copy and a stream add, where we have seen that the saturation point happens before 11 tasklets. In particular for add, happened with 6 tasklets. So what we see here is that there is no performance increase from 8 to 16 because the saturation point has happened before, because this particular scan SSA add is memory bound, which is not the normal thing. The normal thing is that the execution of instructions in the pipeline takes longer, and most of the workloads, as we observe, are most of these workloads on the UPMEM PIM architecture are compute bound, right? So that's it's exactly what you said before. But now you can see it in most of the workloads where we see that the saturation happens at 11 tasklets. Okay, more details in the paper for this analysis on one DPU. Also for the strong scaling analysis on one rank. In this case, we are increasing the number of DPUs. We use the same number of tasklets per DPU that we obtained from the previous experiment. And here in some of the cases, we will have inter-DPU synchronization time, for example, in Needleman-Bunch, my informatics workload, and then speed up over one DPU. And yeah, I'm not going to go very much in detail over the results. You can see that this computer is also slow, and that in most of the cases, when we increase the number of tasklets, all these plots surrounded by the green box, we see that execution time reduces when we increase the number of DPUs. So we are exploiting more parallelism, and that's why we obtain better performance. In some cases, we'll have other issues like load imbalance, or also a lot of inter-DPU synchronization needs that definitely affect the overall performance. We have, three, let me see. Okay, we have 3 examples here. You can see, for example, this BFS, this amount of inter-DPU synchronization is pretty high, and makes that 64 DPUs are even worse than 32, so than 64 are even worse than 16 DPUs. Okay, you can see more results in the paper for strong scaling experiments on 1 rank, on 32 ranks, and also weak scaling experiments. And I want to very, very quickly go over the comparison to CPU and GPU. We identify from this comparison some workloads that are more suitable for the UPMEM PIM system are these 10 workloads here on the left. We are going to very briefly, very quickly discuss what are the common characteristics of them, and then some others that are less suitable. Essentially here, the distinction is that in one case, we are faster than GPU, in the other case, we are slower, but it's because of a reason, and you're going to see what are the key characteristics here. Well, you have some performance numbers that are interesting for sure, but I want to go to the key observation. And the key observation is that the UPMEM-based PIM system can outperform the state-of-the-art GPU that we use in our analysis when the workloads have 3 key characteristics. First of all, streaming memory accesses. Streaming memory accesses means that we are accessing all elements of an array, right? Recall the stream benchmark that we have using our analysis. And when we have streaming memory accesses, the good thing is that we are going to use all data from one chunk of data that we move, a DMA transfer moves from MRAM to WRAM, right? And when that happens, we are exploiting the maximum available bandwidth, right? And this is why the architecture is good at that with these kind of accesses, right? Because we can achieve higher sustained bandwidth. Also, no or little inter-DPU synchronization. You already know that if we need to synchronize across DPUs in some way, this imposes an overhead. In some of the cases, this overhead is tolerable. Some of these benchmarks actually use some sort of inter-DPU communication, but it's pretty lightweight. And also, no or little use of certain operations, those operations that are emulated by the SDK, by the runtime system, like integral multiplication, division, and floating point operations. So if your workload is not, so if your workload has these 3 characteristics, for sure is going to be suitable for the current architecture of UPMEM PIM. Future architectures, I expect them to be better. So 3 characteristics that define when a workload is potentially suitable to the UPMEM PIM architecture. And then here you also have some results for energy comparison. We could only do the energy comparison for the smaller system for, say, certain reasons related to the setup itself that we cannot control. But yeah, also see very good energy results in comparison, especially for to the CPU. And yeah, and finally, some key takeaways. The first key takeaway, it's something that we just discussed. In the UPMEM PIM architecture, most of the workloads are compute bound. It's an architecture that is compute bound. It's most of the workloads are going to be here in the compute bound region because normally we will see that the execution on the pipeline takes longer than the access to MRAM or the data movement from between MRAM and WRAM. And this is why we expect that most suitable workloads are those that are memory bound on conventional architectures. Second key takeaway is that the best, most well-suited workloads for the UPMEM PIM architecture use no arithmetic operations or simple operations, as we have just discussed, and also little or no communication across DPUs. And this is this last takeaway is the one that I showed in the beginning, comparing to CPUs and GPUs. I think that it's a really promising system. It's both UPMEM-based PIM systems that we have tested, the larger and the smaller one, are faster than the CPU in almost all cases. If they are not faster, it's because or either a very intense use of multiplication or floating point operations or inter-DPU synchronization. That only happens for 3 of the benchmarks. Compared to the GPUs, the larger system is significantly faster than the GPU for 10 of the 16 benchmarks, and we also know the reasons why it's not better, not faster for the other ones. And So we know where we should improve the processing in memory architecture to make it more competitive with current GPUs that, as I said, after years of hardware and software optimizations of on GPUs. And finally, probably one of the most important takeaways is how much all these PIM systems can be energy efficient as compared to other processing in memory, processor-centric systems. And this is the executive summary. We have presented the UPMEM PIM architecture, the first real-world processing in memory architecture, and we have characterized it and also studied what are the workloads that are more suitable for this architecture. And as I said, all our codes are available for your use or anyone's. And if you want to learn more, I would recommend you this longer talk that I gave in July. So this is all related to the first part of the lecture. In the second part, lecture 9B, we are going to learn about how to characterize data movement bottlenecks. It's another recent work of us, as I said before. Okay, are there any questions in the meantime? Are there any questions in Zoom or something? Okay, seems that there are no questions. Okay, anyway, you can ask more questions about UPMEM later as well if you want. And now we go to lecture 9B, how to evaluate data movement bottlenecks. In this lecture, what I'm going to present is a methodology that we have developed for the analysis of data movement bottlenecks on conventional processor-centric systems. In particular, we focus on CPU systems. And from this analysis, one important byproduct of this analysis is a benchmark suite. And this benchmark suite can be pretty useful to analyze memory data movement bottlenecks and also for processing in memory studies as well. So first of all, an executive summary, data movement is a major bottleneck in modern systems, as you know, but there are different sources of data movement bottlenecks, and there may be more or less suitable mitigation techniques, data movement mitigation techniques. So traditional ones are caching or prefetching. As you know, these days we start using near data processing as well to alleviate these data movement bottlenecks. But we want to understand what's the best of these choices for the specific data movement bottleneck that we may have in one particular workload. So that's why our goal here is to design a methodology to identify sources of data movement, compare the data movement mitigation techniques, both those that are compute-centric and those that are memory-centric, near data processing. And the approach, the way that we do this is by characterizing many different workloads, many different applications, and propose some key metrics to do this analysis, as you will see. Key contributions of your work, an experimental characterization of 77,000 functions from 345 applications, which is a very large study, as you can see. The methodology that we propose to do the characterization of data movement bottlenecks, and the benchmark suite called the MOVE, with 144 functions that suffer from some sort of data movement bottleneck, and they can be used for later studies related to data movement and how to mitigate or alleviate them. And we also finally show, I'm going to very briefly talk about them today, but you can find many more details in our papers and longer talks given by Geraldo, who is the first author of this work, case studies of where we can use these benchmarks that we have open sourced. And yeah, and that's the URL of the repository. So let's start with data movement bottleneck. Well, I think that we can skip this because it's essentially talking again about the fact that there is a lot of data movement in current computing systems. What do you mean? Oh, we still have the same issue, right? Yeah. Okay, yeah. Yeah, so this is, the data movement bottlenecks, as you already know. And in this work, we are going to compare compute-centric architectures with memory-centric architectures. These are our assumptions, by the way. Compute-centric architectures, we focus on CPU, where we have a deep cache hierarchy with 3 levels of cache. That's something that we are not going to normally have on a memory-centric architecture, where the processing elements or the cores are closer to DRAM, and typically we don't have such a deep cache hierarchy. Recall the example of the UPMEM PIM architecture, where we only have MRAM and WRAM. In this case, we are representing, instead of using a WRAM, which is a scratchpad memory, we use L1 memory per CPU, but in the end, it's a very, very similar setup, as you can see. And this is what we call near data processing, or processing near memory. And we want to study how much near data processing can mitigate the data movement bottlenecks. You already know these. These are slides that I can skip. Real world processing in memory systems. As I said, both are near DRAM banks processing. One of them is general purpose computing. The other one is for neural networks, as I mentioned before, and many different workloads where we can use near data processing, where near data processing is promising. And these are some works of our group as well, showing the benefits of near data processing in different types of applications. So these are things that we already know. Now, the main goal here is to identify memory bottlenecks and classify them in some way. And one thing that we observe is that existing methods to classify memory bottlenecks are not so reliable. Typical ones, if you go to the related literature on processing in memory, you will see that these are 2 typical ways of characterizing the bottlenecks. One is called the roofline model. You're already familiar with it. The other one is the MPKI, which is the misses per kilo instructions. So it's the number of misses in the last level cache per every 1,000 instructions that are executed in the core. And what you are going to see with these 2 is that they don't really capture well what are the sources of the data movement bottlenecks. And also, they are not even completely reliable to predict whether a particular workload is going to be good for a certain type of data movement mitigation technique, for example, near data processing, or something else, right? So, for example, in the roofline model, you remember we have a memory bound area, a compute bound area, and in principle, the assumption is that the compute bound area is not suitable for processing in memory or for near data processing, while the memory bound area is more suitable. And but we did some analysis, and we studied for many different workloads, all these different dots. We executed them, simulated them on a host processor or on a PIM system. And then we compare the performance of these 2. And we see that in some cases, actually, memory bound area, you see a lot of orange dots, which are faster on NDP. And on the compute bound area, you also see some blue dots that are faster on CPU, as we could expect. But it's not in all cases, right? There are cases where the performance is similar on both sides, and there are cases where the performance changes depending on the specific configuration that we are using. For example, number of cores or number of threads that we use in our experiments. And what we see is that even though the prediction is fine for some of the workloads, for others, it's not that fine, right? For these ones here or these ones here, the roofline model is not really predicting well whether something is going to be PIM amenable or not. Something similar happens as well when we check the MPKI in the last level cache. Remember, misses per kilo instruction in the last level cache, and this is increasing from 0 to 40, and this is the speed up over CPU. And okay, so we see that for most of the workloads that are here in this region with high MPKI, they are faster on NDP, which is good. Some of the workloads that are in this region, which is low MPKI, they are typically better on the CPU, but then there are also other workloads, like all of these here, that supposedly are could be better for the CPU because their MPKI is low, but we are obtaining some improvements, some performance speed up from executing on the NDP side. So also this MPKI is not a super reliable way of characterizing the workloads. And this is why we believe that we need a new methodology to identify the data movement bottlenecks and correlate the data movement bottlenecks with the most suitable data movement mitigation mechanism. So we propose a methodology with these goals in mind, and the methodology has 3 different steps, as you will see. And essentially, the methodology is based on analyzing the workloads in different ways, profiling them. And we do architecture-independent profiling, which means that we are extracting characteristics of the workloads that are completely independent of the underlying architecture on the underlying hardware. If you have a workload that accesses randomly or accesses memory in stride, that's an inherent characteristic of the workload. It's independent of the underlying hardware. While in other cases, I mean, for other metrics, we are doing an architecture-dependent analysis. We need to make some assumptions to completely understand some workloads. I mean, assumptions with respect to the hardware that we are using. But yeah, as I said, we use both types of profiling. And this is an overview of the methodology. We have some user input, which is the source code of our target application. In the first step, we do some preliminary application profiling in order to identify regions of interest in our analysis. In the end, we wanted to analyze many different workloads, but the one common characteristic of all these different workloads is that we want them to be memory bound, right? So we first of all start with, I said, more than 300 different applications, and we cannot analyze every single line of code of these 300 applications, right? So what we did is doing a preliminary analysis to identify those regions of the 300 plus applications that are more promising for our analysis. So already can say that they are memory bound. We do this in step 1. In the second step, we do something that we call the locality-based clustering. This is the architecture-independent part where we analyze the data locality, the spatial and temporal locality of the workloads. And then we do a step 3 where we go deeper into the analysis and the characterization of the different memory bottlenecks. And we do that by using a scalability analysis. It's an analysis where we compare execution on a conventional CPU with execution on some type of near data processing, and we change the configurations in them using, for example, different numbers of cores on both sides. And that's a way of, we see how the workloads scale as we increase the number of cores, and based on that, we characterize the memory bottleneck. That's more or less what we did, and this way we are going to find a number of classes of memory bottlenecks. So let's take a closer look at each of them. First step, application profiling is like, oh, I want to analyze many workloads from different important domains, important workloads, modern workloads used these days. I want to see, okay, I have this whole application, where should I focus? What part is the most interesting for it? So what we do is some hardware profiling on a real CPU system, and in our case, we use Intel Vitium, but there are other different profilers that you can use, like PERF or gprof, or if you were doing this analysis for a GPU, for example, you can use MBProf or other GPU profilers. And in Vitium, there is an interesting metric that is called memory bound. And this memory bound tells us the percentage of cycles that the CPU pipeline is stalled due to access to data. So it's a kind of a relevant metric that we are obtaining from Vitium. But as I said, you can also find similar metrics in other profilers as well. So that's the first thing. By the way, you can skip this step completely if you already know what part of your application you want to analyze, right? So if you want, so you have the suspicion that one particular portion of your code is memory bound, you can just go to step 2 directly. And in step 2, we analyze this code by obtaining the temporal locality and the spatial locality. And this is architecture independent, as you will see. For the spatial locality, what we create some kind of a stride profile histogram. You guys are familiar, you know what's a spatial locality, right? In some sense, it gives us the probability of accessing some address that has been accessed. Accessing one address that is neighboring to an address that has been accessed before. Imagine that we have this memory trace, 0, 1, 2, 3, 4, 5 are the addresses that we are accessing, and after accessing address 0, we access address 1. So we see what's the distance between these two addresses, and we see that the distance is 1, right? So we increase in this stride profile histogram, we increase the bin corresponding to 1 because the distance between these two is only 1, right? So this way we create one histogram for the stride profile. This is an example of low spatial locality because you can see that, you know, maximum, for example, occurs here at distance 8. And this is an example of high spatial locality because the strides tend to be closer to 1, as you can see. And then we do something similar for the temporal locality. Temporal locality is how many repeated accesses I have to the same address. And in this case, we have a reuse profile histogram. And we say, okay, in this window of time of the execution, how many times did I access this address? 4 times. Okay, so I increase by 1 the bin corresponding to 4 accesses in a certain window of accesses or cycles, right? And this is the profile histogram. This would be low temporal locality because, you know, there is not much reuse. This is high temporal locality because there is much more temporal reuse of the same addresses. So by using these two, you will see the results later. Now, let me describe briefly what the step 3 consists of. It's extracting some important metrics that we identified as useful for the characterization of data movement bottlenecks by using this scalability analysis. And the first of these metrics is the arithmetic intensity. We have already talked about the operational intensity, or also called arithmetic intensity in the roofline model. Essentially, it is the amount of computation per data access or per memory request, or in the previous lecture, we saw it's the number of operations per byte. In the end, it's always the same story. Another important metric as well is the misses per kilo instructions that we have already defined and used before. And a new metric that we propose that is called last to first miss ratio. And this is essentially the ratio of misses in the last level cache per misses in L1. In some sense, what this metric is going to show is how much an application can benefit from L2 and L3. So if the last to first miss ratio is high, it's because so if it's high, it's because we have many misses in the last level cache compared to the L1. What this means is that the cache hierarchy is not being useful. If it's low, it's the other way around. So if it's low, it's because whatever misses in L1 hits normally in L2 or in L3. So what means is that the cache hierarchy is working well. So that's why this metric is useful, as you will see. In the step 3, we use 2 different configurations. One is a host conventional CPU configuration. The second configuration is the NDP system, where we assume that we have some cores near DRAM. And now let me clarify very briefly the assumption. Even though this is architecture-dependent analysis, because we are doing simulations here, and we need to assume some organization here, some CPU architecture, some characteristics of L1, for example, cache line size, and many more things. We try to keep it somehow architecture independent, because the only thing that we change from this configuration to this configuration is first the fact that the cache hierarchy is different. Here we have a deep cache hierarchy. Here we only have a single level of cache. And the second one is that we are closer to memory in the configuration number 2, which means that we can exploit higher bandwidth and lower latency. But the core itself is the same type of core. Even if we might be evaluating configurations here that wouldn't be realistic in a real PIM chip fabricated on whatever technology, that's not our goal here. We are not evaluating realistic processing in memory systems in this work. What we are doing is evaluating workloads, analyzing them, and understanding them. And this is why we want to keep the specific characteristics of the processor itself away from this analysis, and only as much as possible focus on the impact of data movement mitigation techniques like cache hierarchy or the higher bandwidth in processing in memory architectures. So yeah, that's what we did in our scalability analysis. We changed the number of cores on both configurations from 1 to 256. That's why, right? It's it's not easy to have a 256 core out of other processor near DRAM. That's what I wanted to say. Okay, and we use 3D stack memory as main memory in our analysis. Okay, so now next 3 sections of the presentation are about step 1, step 2, and step 3. But now you're going to see some performance, some results of the analysis. In step 1, as I said in the beginning, we analyzed 345 applications from different domains, and we select some of these, the functions that take part of these 345 applications by using Vitium. And actually, these are the selection criteria that we use, memory bound metric being greater than 30%. And in total, we find 144 relevant functions, interesting functions. And what we do is we apply steps 2 and 3 to the 44 functions to, let's say, create our methodology, propose our methodology, and then we validate our methodology with the rest 100 functions. Now that we are already done with step 1 and we know what are the interesting functions for us, so these 144 ones, we go to step 2 and analyze the locality. In this case, remember how we obtain spatial and temporal locality metrics, and we paste, well, I mean, we put the values of temporal and spatial locality for the different workloads in this 2-dimensional plot. And this way we see that those bluish ones are high temporal locality, these ones are low temporal locality, and here on this side, low spatial locality, high spatial locality, as you can see. In principle, we are going to expect that those workloads that have lower locality, both spatial and temporal locality, more or less in this region, would be more amenable to processing in memory. And they are, because they are less likely to take advantage of a deep cache hierarchy. Why is that? Because they have lower spatial and temporal locality, so probably they won't benefit much from caches. Yeah, and that's the second step. And in the third step, we do the memory bottleneck analysis. And in the memory bottleneck analysis, we extract these 3 important metrics, and we combine these 3 metrics with the temporal locality that we obtained in the previous step. One thing that we notice here is that temporal locality is more relevant than spatial locality, at least in the configurations that we tested. And the reason why this happens is because if you look at the 2 configurations that we are evaluating, the host and the PIM configuration, they both have L1 of the same characteristics. And normally L1 is where most of the spatial locality is captured. So that's why in our analysis, spatial locality is not so relevant, temporal locality is more. And we create this kind of tree to do the classification after, having simulated and very thoroughly analyzed all the data that we obtained from our simulations, from all these metrics, we came up with this way of classifying the workloads. Depending on the temporal locality, whether it's low or high, you go that way or this way. If it's high, for example, you check the LFMR. LFMR might be low, which means, remember that the cache hierarchy is working well on the host side, or maybe the LFMR is increasing when we increase the number of cores in our experiments, when we do our scalability analysis, and then we check the MPKI values and we check the AI values, and based on that, we obtain 6 different classes of memory bottlenecks. The first class is applications that are DRAM bandwidth bound. So they are, in the host execution, they are essentially bottlenecked by not obtaining enough bandwidth from memory. In other cases, it's latency, they are latency bound. In other cases, it's because the capacity of L1 and L2 is too limited to mitigate the data movement enough. Then we have class 2A, which is applications that show contention in the access to the last level cache, or applications 2B, those that are constrained by the size of the L1 cache, and finally, those that are purely compute bound workloads. So as you will see, those are always going to run faster on the conventional processor-centric architecture. So these are different data movement bottlenecks, and we can talk in a little bit of detail about any of them. Did you guys have any questions about the previous steps? Okay, yeah, go ahead.
When you defined on the graph the scale from 1 to 0 to 1 on the grid for spatial and temporal locality.
Yes.
How did you get them within a range of 0 to 1 from these sort of 0 to 1?
Yeah, that's I've shown you that when I defined the spatial and temporal locality. Yeah, there was a graph. So essentially, you get some scores from these plots of histogramming, and then you normalize from 0 to 1. So that's more or less how it is. In order to have something that it's normalized for all workloads that we analyzed. Okay, it's a kind of a common way, and actually the way that the metrics that we use for temporal and spatial locality are not proposed by us. We are taking it from previous work, and it's one definition of temporal locality or spatial locality, one way of measuring it. There you can find other ways as well that could also be valid for our analysis. For example, another metric that is typically obtained to measure temporal locality is the reuse distance. You might have heard of it. The reuse distance is another way of measuring the same thing. I have an access to address A here, to address A here, and in the middle there is a certain distance, which is the number of memory accesses that have happened. It's a different way of counting the temporal locality in this case, but the purpose is exactly the same. Okay. Yeah, so this, our first class is class 1A, DRAM bandwidth bound. What we notice here, observe that here on the top right, we have the value of temporal locality, LFMR, MPKI, and AI for the different, these metrics for the different workloads. And here, you see some results. These are for host, performance results and bandwidth results, and these are for NDP, for the near memory side. As you see, at some point, the performance and the bandwidth in the host, when increasing the number of cores, saturates, while the NDP side is able to keep exploiting more bandwidth, and this way increasing the performance, as you see. So NDP scales without saturating due to the bandwidth. So these are DRAM bound applications and NDP does clearly better than the host side. In this class 1A, also we can observe in terms of energy consumption. So notice that we are saving a lot of energy because we don't need to, go to L2 and then L3 and then go through an off-chip link that also consumes a lot of energy. Here, it's essentially like accessing DRAM, right? Which is more or less the same amount of energy that you also needed in the host to access DRAM for the, DRAM access itself, internal to DRAM. But yeah, as you see, we can save a lot of energy regardless of the number of cores that we use in both configurations. Then we go to 1B. In 1B, these are DRAM latency bound. One thing that we notice is that the LFMR is high, so L2 and L3 are quite inefficient. Yeah, we see that the NDP execution, this is normalized performance for both host and NDP for different number of cores. So for any number of cores, we observe, well, here it's quite similar, but yeah, let's say the benefit of NDP increases when we increase the number of cores, as you see. And this has one reason, and the reason is that for these workloads, the access, so these workloads benefit from the fact that in NDP you have much shorter latency compared to the execution on the host. And this also happens consistently for all number of cores. And this is why these workloads are DRAM latency bound on the processor-centric architecture, and they also benefit from the execution on the PIM side. The third type is 1C, or third class is L1, L2 cache capacity. So in these ones, we see that the LFMR decreases as we increase the number of cores that we use in the experiment. And what this means is that L2 and L3 turn more efficient. In the configuration that we are using in these experiments in particular that you see in this slide, not because in the paper we have even more experiments. Here, we are using private L2 caches for the cores. So as we use more cores on the CPU, the total amount of cache in the system also increases. And because if it increases, the workload execution benefits from that. So that's why we see that for NDP, it's better, it's faster for lower number of cores, while for higher number of cores, it's the host that is faster. But that's because of the effect of more cores, more cache capacity, and then a benefit for this type of workloads. We also see in this plot, it's the latency for the host and NDP when it comes to 64 cores, which is a higher number of cores. We see that this latency, total latency is of the access to memory, over the access to data, is smaller, is lower in the host than in NDP. And that's because we have more hits in L2 and in L3 due to the higher total or larger total cache capacity. And that starts happening, for large number of cores, as you see. For a smaller number of cores, NDP still provides lower latency. Then we go to class 2A, which is L3 cache contention. What happens here is that when we increase the number of cores, when we increase the number of threads executing the workload, LFMR increases. And this is because L2 and L3 turn inefficient. And why is that? Because there is contention in the access to the caches. That essentially depends on the characteristics of on the specific access patterns of the workloads, right? So here, the more cores, the more conflicts we have in the cache, and that's why that's what degrades the performance of the host. And that's why NDP maybe in the beginning is not that good, but at some point it's better to use processing in memory rather than the processor-centric approach. So that's what you can essentially observe here. And also how, as I said, the caches turn inefficient when we increase the number of cores. And this makes, you can see in this plot, where the memory requests are satisfied. Here it's L1, L2, or DRAM. As we increase the number of cores, we have more memory requests being satisfied by lower levels of the cache hierarchy, L2 or L3, or even worse, DRAM, right? So the higher number of cores, the more frequently we have to go to DRAM, and this is what makes that this particular class ends up being good for NDP for a large number of cores. Then we have class 2B, L1 cache capacity. Here, the observation is that caches are quite efficient, L2 and L3 are quite efficient, and memory intensity is low, but they have also low AI. In general, the performance of both is pretty similar for the workloads that belong to this class. So yeah, in the host execution, you get the benefit from having L2 and L3. In the NDP side, you get the benefit from being closer to memory, and this makes both make that the performance is more or less the same for any configuration. And yeah, in the end, these are L1 cache capacity bottleneck applications, because L1 is what is. It's L1 what determines the latency of the memory accesses in most of the cases, in most of the configurations. So L1 is the main bottleneck here, and this essentially happens in both parts, in both sides, in the host side and also in the NDP side. And finally, compute-bound applications, class 2C, where these are for sure good at exploiting the deep cache hierarchy of the CPU, and they also have high arithmetic intensity. If you have higher arithmetic intensity or operational intensity, means that you're using the core a lot, and you don't have to go so frequently to memory to grab more data. So in the end, if your processor, you have a powerful processor like out of order CPUs, or this could also apply to some GPU workloads as well, you see that the performance is already quite good, and that's why in these cases NDP is not really a good fit. So this is our bottleneck analysis for 6 classes. Even though here we have analyzed CPUs and we did an analysis that makes some assumptions about the underlying hardware and architecture, this type of analysis, we believe that this it's kind of exportable to other processing, to other systems and other configurations of both the processor centric approach and the memory centric approach. And yeah, and actually that's one of the things that we show in the paper as well, because here the results that you see are for out of order cores, but we also observed similar behavior for in order cores. So different types of processors also provide very similar characterization of the workloads. And then we validate the methodology. The validation of the methodology is in 2 phases. The first one, it's focused on the 44 workloads, and what we have to define here is the threshold, right? I'm saying MPKI is low or MPKI is high, or LFMR is low or LFMR is high, right? But yeah, I need to define what low and high means, right? And to do so, we define this threshold by doing the analysis of the 44 workloads. And after having done that, we evaluate the methodology, we validate the methodology using the rest of functions that we identified in the very beginning. And what we observe is that our methodology is quite good, because for these 100 functions, 97% of them are correctly classified according to, or using our methodology and according to the 6 classes of memory bottlenecks. And you can find more in the paper, more analysis about the effect of a different size of the last level cache, summary of our workload characterization methodology, also for in-order cores, as I said, on both the memory side and the processor side or host side. And then some limitation of our methodology and also some analysis of the benchmark diversity, because one product of this is the benchmark suite that we release publicly. And this is the paper. And then we also have in the paper some case studies, because remember from previous lecture and also the beginning of this lecture today, we talk about things that still need to be enabled to make, or things that still need to be developed to enable processing in memory. And what we provide in this work is something that can help on that. We have open source and simulation infrastructure. We have open source benchmark suite, and also we are proposing a methodology to do the analysis of the workloads and see which of them can be more PIM suitable or less PIM suitable, right? And there are many different things that are, yet to study. And all these things are in the book chapter that we have mentioned several times over the course of these lectures. And these are some examples of the case studies, like, for example, load balance and intervault communication on NDP. One thing that we observe in this analysis is, in this case study, is that many or a significant portion of the memory requests of a near memory processing core need to go to remote vaults. Recall this problem, or bottleneck that we have in the UPMEM PIM architecture with inter-DPU synchronization. If I need a DPU to access data that resides on the memory of another DPU, I will have to incur a significant overhead, right? From going through the CPU to get data from another memory, right? And one thing that we observe in the analysis here is that that's not infrequent for the type of workloads that we analyze in this work. So for sure, in the future, it will be very good to enable better ways of communication and more efficient ways of communication across processing in memory cores. Then we also analyze different architectures, right? We talked before about out of order, in order cores, and we also study how all methodology can be good or bad for accelerators as well. And it's interesting that the characterization of the workloads doesn't change significantly, or essentially doesn't change if we do it for accelerators instead of general purpose cores, which means that the methodology is good. Then we try different core models as well, in order cores, as I mentioned before, and finally, different ways of doing the offloading, fine-grained NDP offloading. You remember the PIM enable instructions paper, right? So that's what we did here, was going deeper in the analysis using the benchmarks that our work produced. And in this analysis, we check individual basic blocks in the code, which are in the end are like a very few amount of instructions. And we noticed that there are a few basic blocks that are responsible for most of the last level cache misses in the execution on the CPU. And what this means is that it's certainly possible, at least for many workloads, to isolate a short piece of code and create a PIM enable instruction for them and offload only this PIM enable instruction. So that's essentially the idea. And we believe that this is something that still requires and deserves more exploration. So yeah, that's essentially what it is. And just to give you a little bit more about the analysis that we did is, one of these use cases or case studies for NDP accelerators. These are the two configurations that we are evaluating: compute-centric accelerator that accesses memory through the off-chip link, or the NDP accelerator that resides, for example, in the logic layer of a 3D stack memory. And here you see some performance results for 3 example benchmarks from 3 different classes. And it happens as expected, right? For A1, for 1A and 1B, we see that the performance on the memory side is significantly higher than on the CPU side. For the truly memory-bound workloads, for the compute-bound workload that we have, performance doesn't change, because in the end, they are already doing well. They don't benefit from more bandwidth or from lower latency to memory. So that's what we can see here. And you can for sure find many more details in the paper. And that's all, I guess. This is a repository where you can find the benchmarks and the simulator. This is the link to the repo. And the conclusion is that data movement is taking a lot of energy and execution time in current computing systems. And it's really desirable and necessary to characterize the data movement bottlenecks in order to propose specific solutions for these or specific data movement mitigation techniques for these different bottlenecks, right? And that's what we do in this work, proposing a methodology and performing a large workload characterization. And we have open source a simulator and a benchmark suite that can be useful for future studies on processing in memory. And if you want to learn more, I would recommend you this seminar that Geraldo, that blonde guy there, gave a couple of months ago, and you will learn much more. And also, probably he will also give a lecture in the PIM course that we teach on Tuesday evening. So this is all from my side today. I'm really sorry about the inconvenience that we had with the computer and so on. I hope that Zoom folks are following our lectures and they see how many issues we experimented today, and they figure out a solution. Any questions? Yes.
A quick question. So in the previous classification graph, why not using the arithmetic intensity as the first criteria? It seems that if the AI is high, then the task is not data bounded.
Yes. You have to start your lecture? You are going to teach now, I guess.
Yes.
Okay, very good. Yeah, I can tell you outside. Okay. Thank you very much, everyone. See you soon.
But officially it's until 4.
Officially it's until 4.